So what I want to talk about today is the finite element method, or start talking about. Often you hear just the acronym FEM or FEA, like finite element analysis. And that's a super general method. So it's in general, if you go to Wikipedia or some, you will find that it's a method for discretizing partial differential equations in general. And the typical path you will see in like a textbook is that it starts from a variational problem. So first, I guess I should explain what is a variational problem. It's actually very similar to what we were talking about optimization. In optimization, we are minimizing some function like this, where the understanding was that this x is discrete, okay, has some n degrees of freedom or something like this. Variational problem is the continuous analog of this, okay, and that means that we are not minimizing over some discrete number of degrees of freedom, like 10,000, but we are minimizing over a function, okay. So this thing is called a functional. So let me try to explain that. If I have a function from an interval 0, 1 going to real numbers, an example of a functional would be an integral. Okay, integral from 0 to 1, fx dx. Because what the integral is in terms of types, the integral actually is a mapping from a function. Okay, so this is the type of the function, and it maps a function to a real number. Okay. So like from point of view of programming languages, it's something that takes a function and outputs a number. And what it really is, it's a generalization of this where this n is infinity, okay? So it's arbitrary, we could say continuous or smoothly differentiable or whatever, but the point here is that this function has infinitely many degrees of freedom, okay? So the functional is a mapping from a function to a number. And now you would be, and a variational problem means, and there is a theory to it called the calculus of variations. That means minimize functional, typically subject to some boundary conditions, okay? And once you have this, some problem of minimizing some functional, then the analog of basically here we had saying that the gradient needs to be 0, if I'm to simplify some of the details. The analog in the calculus of variation is called Euler Lagrange equations. Or Euler Lagrange equation. What the Euler Lagrange equation does, it converts the variational problem into a PDE, partial differential equation. Okay? And then finally, oh no, then there is one more step. Then there is apply dot product with test functions. Okay. So basically you integrate both of the sides of the PDE against some set of test functions. Okay. By the way, none of this you need to remember. I'm just telling you what is the usual exposition you can encounter in books, so you're not surprised. Then you apply test functions, which means you integrate both sides of the PDE. And then finally, you apply finite element discretization to this. And you get a discrete problem to solve. So why I'm saying all this is just to show you that this standard path is pretty complicated. And I will give you a simpler introduction to finite elements. Basically what we are gonna do, so we're gonna do none of this, okay? We will do basically just this last bit. That's what we are gonna focus on. So what I wanna show you is how to use finite elements to discretize the functional directly, okay? How to convert continuous things to discrete things, okay? So actually, pragmatically, let me connect it to what we had before, okay? What is our goal? Why do we even need the finite elements? So we talked a lot at the beginning of the course about the equations of motion in Hamilton's form, right? So you very well remember this formula, right? Those are the equations of motion. That's basically what all phase-based is about. This J matrix, that's the trivial 2n-dimensional rotation, right? So it's all about the Hamiltonian, right? And the Hamiltonian is nothing but the sum of the potential and the kinetic energy, right? So what we will use finite elements for is to build better versions of the potential and of the kinetic energy. Okay? Basically, another way I can explain this so far what I have showed you, or so far what we have done, we just assume that both E and K correspond to mass spring systems. That's what you have been already playing with. I told you that's the simplest physics-based system you can already start simulating. It's pretty simple, right? If you have some object you want to be simulating, then you just place some mass points on the boundary, on the interior, right? And you somehow connect these mass points using a set of springs. And that gives you some physics-based system, which you know how to define the potential, right? We talk about Hooke's law or the STVK springs. And you also know how to define the kinetic energy. That is super easy, right? That's 1/2 mv squared, where m is the mass of each of the mass points. So those are the mass points. Then there are stiffnesses of the spring. So you all know how to build these potentials and kinetic energies for a mass spring system, right? So this works, but it has some problems. What are actually some of the problems with this approach? I think we even discussed that before. Like, why don't we just end there? Why do we want to do something more fancy and go to finite elements? So one problem is that this is they're kind of philosophical, I guess. But well, no, they are also very real. Any ideas? So one, yeah, hey, James.
So you can have instead of having a system with many variables and many degrees of freedom, you can have sort of a chunked out system where each you consider only the inputs and outputs of one small subsystem at a time.
Yes, if I understand you correctly, basically it's kind of oversimplification of the thing you want to be modeling, right? Like the assumption that this is some sort of real world object, like the human body or a piece of rubber or something like this, or it could even be a rigid body, right? And if you are doing the mass springs, then you basically just place the point somewhere, and then you say, hey, all the mass is actually concentrated at these points, and then you connect these points with springs. So actually not simulating like an actual continuous object, you're actually simulating like isolated mass points which are connected in some special ways, right? So that's the one funny thing is that mass is concentrated at the points and there's like nothing in between them. That's really what you are simulating with a mass spring system, right? The other problem is that the results you will get depend on the directions of the springs, right? Because you have, even actually when we talked about cloth, right? If you are doing like a cloth simulation, and let's just do like a very coarse grid, then we said that it matters, maybe let me draw a different color. It matters how exactly you design those springs, right? If you put all the springs like this, then the cloth will be more resistant to stretching exactly in this direction, right? Then you can put other springs like this, for example. But whichever way you put the springs, the dynamics, the motion of the object will be biased towards the directions of those springs, okay? And that's why it gets kind of tricky, and you can play with different designs of the springs. Even worse, if you're not happy with the resolution, so here like 4x4 cloth would probably not be enough, right, to get nice wrinkles and stuff, you need to increase the resolution, right? And if you increase the resolution, what you will find that the parameters you have tweaked before, the spring stiffnesses and the masses, they might no longer work. So you need to retweak those parameters. And that is a little bit annoying because then maybe you need to change, then you increase the resolution and you see, oh, now it looks beautiful, but it runs too slow. So you need to decrease the resolution again and find yet another set of parameters, okay? So the mass spring system, don't take me wrong, they work. They are used in major production studios for physics-based effects. So if you know what you are doing, if you have enough experience, how to set it and so on, you can get beautiful results with that. But you can avoid these problems of mass spring systems by doing finite element discretization instead. So let me give you like a gentle introduction to this. So let me start with the basic idea, or maybe like a toy example. I guess my point is that I would like to communicate the key idea, which normally gets obfuscated in lots of mathematical details. Okay, but the key idea is actually very simple. What is the key idea? The key idea is to approximate continuous functions with finite number of degrees of freedom. So what do I mean by this? Let me explain that on an example, and actually the same I started with. So let's just talk about one-dimensional functions defined on an interval between 0 to 1 with arbitrary real value. Okay, and let's talk about this integral. Told you before that's a simple example of a functional, something that takes a function and returns a number. And of course, you can look at it like this, right? From 0 to 1, there is some function. And the integral is the area below that function, right? It could be negative, that would be negative area, that kind of doesn't matter. Now the problem is that there is infinitely many functions f, okay? So we cannot really directly compute them on a computer because computer always has a finite memory. Computer always uses bits 0, 1, right? It doesn't have a concept of a general continuous function. So what we are going to do, and that's the key idea of finite elements, we are going to take this interval 0 to 1, and we're going to chop it into pieces. Okay, we are going to chop it into small pieces. They don't have to be equally distributed, so we create these nodes. Okay, and that's very similar to what you do with a mesh in multiple dimensions. Okay. And what is important are these little pieces here, because those are the finite elements, essentially. So the idea is to approximate this problem. Let me say that better. So these red points are nodes, okay? And with each of the nodes, I associate what is called a shape function. So let me draw it again. So this will be my interval 0 to 1, okay? And I insert some nodes in between. Again, they don't have to be equally spaced. And for each of the nodes, I define a shape function. So what's a shape function? That's basically an interpolation from the nodal values to everywhere on the domain, in this case the interval 0, 1, okay? So the first shape function, I'll show you, I'm drawing here piecewise linear shape functions. So the first shape function is going to be function S1. S1 is a function from the same interval to actually also just 0 and 1, okay? Then for the second node, I'll draw it in blue, I'll have another shape function called S2. That is S2, and S2 says the same thing, okay? Goes from the entire interval to 0, 1, okay? You probably get the idea. I'll just draw one more. Here will be, oh wait, wrong. That was supposed to be here. This guy here is gonna be S3, okay?
So this is kind of like a radiant basis function almost. Are you constructing a shape out of a bunch of smaller functions?
That's exactly right, James. Yes, okay. That is one way how you can look at this. That you can look at this space of functions as an infinite dimensional vector space. And what I'm doing a finite dimensional subspace of this space. And then I will say that I will approximate these functions by projecting on this subspace. So if you are solid in linear algebra, you can think about it this way. What I'm presenting here is kind of more like an intuitive way of thinking about it. This is, after all, just a toy example. But yes, you're right. The idea is to approximate an arbitrary function f as a sum of these shape functions. Okay, so, and here this is really all there is to finite element. The idea is to approximate the function f as a sum over all my nodes. So I denote them with index I, let's say, I don't know, from 1 to n, that doesn't matter. Here are the nodal values, and here are the shape functions, okay? So the nodal values, they are just numbers, scalars, okay? And the SIs, they are functions. So this is a linear combination of functions, of shape functions, okay? Exactly of these piecewise linear hat functions, okay? This what I draw here that corresponds to piecewise linear shape functions. But they don't have to be piecewise linear, okay? What you want from the shape functions is that they are locally supported, or should be. They don't even have to be then. Actually, I guess the main thing you need from the shape functions is that they interpolate the fi values. Okay, that's kind of clear from this, right? Because what you are gonna do, so those are my shape functions, or the piecewise linear shape functions, and then you just scale each of them by some coefficient, okay? And the result you get out of this is an approximation of this arbitrary function, and that approximation, let's pick another color, that basically looks like this. Or you tell me what that approximation is. What is that approximation? So here is the situation. I have some arbitrary continuous function f, okay? And I tell you, okay, let's use these piecewise linear shape functions. So they're defined like this. And what are the optimal fi's, and how does the finite element approximation of the function f look like on this example? And what the fi's should be, so I get a good approximation, right? I could get a terrible approximation if I picked all the fi's to be 0, right? But why would I do that? I pick the fi's reasonably. What's a reasonable choice in this example? Is this clear? Shall I make it bigger? Or yep, Jim?
You could pick an fi that's equal to the function at that point.
Exactly, yeah, and that's why I draw these little cyan dots here. So yeah, I can exactly pick. So I guess you could give this some coordinates, right? I could just call this, I don't know, I could call this x0, x, or maybe x1. Could call this x1, this x2, this x3, this x4, and so on. And then I could just say that fi is going to be really nothing but the sample of f at xi, right? And if I do this, then this linear combination corresponds exactly to piecewise linear interpolation, okay? So these dots here are the samples of my function. Those are the fxi's. And then this thing here is just connecting them with lines, okay? Super simple. So I connect all these with lines, line segments, I should say. Okay, is that clear? Because that is the key idea. And then now, once I have this approximation of the function, then I can approximate my functional, right? So because if I have my integral, and I know that this f of x can be written like this, then I can just plug it in there, right? So let's do that. So here is the sum over I fi si of x dx, okay? Now I know that integral is a linear mapping, right? So I can also rewrite it like this. And here I have just the integral of the shape functions themselves, okay? From 0 to 1. But these shape functions, they are given, okay? The only thing that changes, the only thing that depends on the function I'm approximating are the fi's, okay? So these things are constants, so I can pre-compute them and call them wi, and that they're going to be just some scalars, okay? So this thing is approximated as fi wi as a sum, okay? And that's something I can feed to a computer. Brian?
Does each shape function refer to the triangular area in your piecewise example? When you take the integral of each shape function, I mean, is it referring to the triangular area you drew under?
That's exactly right. That's exactly right. So let's talk about the S3, for example. So the S3 is almost everywhere 0, right, on this interval, except for this piece between x2 and x4, right? And there is this triangle. So that integral I have here for the case of S3 would be exactly this area. You're totally right. I'm glad you brought that up. There is one more property I guess I should have mentioned. This interpolation means that the sum of all the shape functions should be what? You can kind of see it from this figure. I'm glad you are getting some geometric intuition. 1, exactly. And that's so it actually correctly interpolates the values, right? Because this kind of means if all the values happen to be 1, I should get 1 back, right? So, and you can also see this nicely on the picture. If I just sum all of them together, I just get a constant 1.
Okay, you're integrating between 0 and 1.
Mm-hmm.
Are you saying we've normalized our function so that interval between 0 and 1 is 1?
No. So I'm still so first, if I'm integrating the S3, it's clear that when if it's 0 over there, then the integral does nothing, right?
Yeah.
That's not what you were asking, right? This has nothing to do with the integral. This is just the shape functions themselves summed together. Okay, and this is just linear interpolation. This is as simple as that. If I give you a value at x1 and a value at x2, how we are gonna interpolate them? Right. So I see what you are asking. Basically, the shape functions are a conversion to the interpolation weights between f1 and f2, right? So if I give you a value of f1 and you want to interpolate it with f2, then you do it like this, right? And the question is what the t is, and the t is exactly the shape function. Okay, so in my case, this would be s1 f1 plus s2 f2. And because if I had just 2, right? If I say that s1 plus s2 equals 1, then from this you can see that s1 is 1 minus s2, right? So I can call it t. So it is the same thing. So another way you can see these SIs as an abstraction, so we don't have to worry about the rescaling of those things. Like this x2 would be like, I don't know, like 0.2 or something like this, right? And you could figure out the interpolation using the 0.2, but it would a little bit ugly. So this SIs, the shape functions, are a useful abstraction over that. By the way, the S functions, the other thing the shape functions should do, first they should interpolate, of course, and second they should be local. They don't have to be, but usually they are. Almost always they are, actually. By local, I mean that every shape function influences only a small piece of the domain, as you can see here, right? The S3 only affects the part of the function, the part of the interval or your domain from x2 to x4. By the way, they don't at all have to be piecewise linear, okay? Any functions will do. They can also be piecewise constant, by the way. So piecewise constant would mean that you have, if I have an interval from 0 to 1 and I can chop it into some pieces, the piecewise constant is actually even simpler case. So that means I like the green one, so I'll keep using the green one. So the piecewise constant would mean that it's almost everywhere 0 except for a constant 1. Okay, this is like 1. This, except for 1 on some, let's say, x2 to x3. Okay, that is also perfectly valid shape function. Now, one thing you can notice that this shape function would not be continuous, right? There is this discontinuity, the jump. These piecewise linear ones are continuous, but they are only C0. Their derivative is no longer continuous. Everybody sees that. So sometimes you actually, what you want, sometimes, not very often, are higher order shape functions. So they don't have to be piecewise linear. Your shape functions could also be, and let me draw this here, they could also be something like this. Okay, something nice and smooth. That's also possible. Those are called typically higher order shape functions or higher order finite elements. Popular ones are quadratic or Bezier or something like this. I won't go into that, but I just wanted to tell you that that is entirely possible. Okay, so there is some creativity in choosing the shape functions. All right, so this is really the key idea, and now we will apply it to physics. Okay, this is the key idea of finite elements. So, is this clear? Can we move on? You had some very good questions there, so that was helpful. So the second step is computing or estimating kinetic energy. Using finite elements. So the motivation is obvious, right? It's the physics is about the Hamiltonian. The Hamiltonian is about this potential energy and the kinetic energy. And excuse me. The kinetic energy is the simpler beast, so we will start with that. And once we are done with that, then we will talk about how to apply finite elements to the potential, to elastic potentials. Okay, that will take longer. That's what we will get to next week. That's a little bit more complicated. All right, so let's talk about the kinetic energy. So we have some object we are simulating. Okay, let's say this is an omega, and it's a subset of either R2 or R3. Okay, either we are doing 2D simulation, or we are, in which case this would be some sub-area, or we are doing 3D simulation, this would be some piece of volume. All right. It's always a manifold of codimension 0, so we are always doing a 2D shape in 2 dimensions or 3D solid in 3 dimensions. Okay, we are not, let's not complicate it by discussing the cases like rods or thin shells in 3D, where the codimension would be 2 or 1. Okay, so we'll just consider these cases. Either we are in R2 and this is some part of a plane, or we are in R3 and this is a subset of a volume, like a volumetric solid. Actually, the nice thing about finite elements is that it works basically the same way for any dimension. So that's why I'll discuss both the 2D and 3D cases at once. All right, so in the continuous world, what is kinetic energy? In the continuous world, so no discretization yet. So the kinetic energy is an integral over the domain. That's this omega thing. And what do I integrate there? So the assumption, this is some body I'm simulating, right? It's moving in space. And it has some kinetic energy. So to be able to talk about kinetic energy, I need to talk about density of that object. So I need to have a function rho, which is a function that for every point P gives me the density. So I guess I could write it like this. I could write it as mapping from omega to, I guess, R plus, right? Density should not be negative. And the other thing is I have a continuous velocity field, okay? So that will be to RD, either 2 or 3. The density, you could make it simpler. You could say that the density is constant over the entire body, but the velocity most certainly, or most frequently won't be constant, right? Even if you have just a rotating rigid body, the velocity field is not constant, right? It depends where the axis of rotation is, but it definitely changes, right? So with this setup, what is the kinetic energy, the continuous one? Those of you who did physics, continuum mechanics should remember this. In the discrete world, it's mv squared, right? So here we don't have mass, here we have density. And you know that mass is the integral of density. So that's why I started with an integral. So it is the integral of the density at some point and the square norm of the velocity, dp, okay, where p is like some arbitrary point here, and it's integrated over the entire domain. That is a continuous formula for kinetic energy, okay? Now, then the main thing I want to do is discretize this formula using finite elements. And what this will give us a mass matrix And that also tells you how can we generalize. Oh, before I was kind of ignoring the masses. I kind of wanted to make everything simple, so I just said, okay, let's say all the masses are unit. In a mass spring system, it's kind of fine. You can say that all the mass points have unit mass, so why make things more complicated? But in general, you want to be simulating something that has possibly even like spatially varying density, right? That the density is not constant over the entire body. If you are simulating something like the human body, then in the lungs there is air, which is a very different density than the rest of the soft tissues, right? So you definitely want to account for that. So this analysis, the finite element approximation of the continuous kinetic energy, that will give us answers to exactly this. All right, so how are we gonna do this? So the first thing we need to do to be able to do this, the first thing we need to do is the analog of, why did this? Oh, there we go. The first thing we need to do is to do the 2 or 3 dimensional analog of this chopping into subintervals, okay? This is like a 1D finite element case. When I took an interval, that was my domain. My omega was this 0, 1 interval, and I chopped it into pieces, okay? Well, I need to do the same thing here. I need to take this domain and chop it into pieces, okay? So I create some nodes on the boundary, on the interior of the domain. By the way, here is an interesting thing I can explain you as I'm drawing this. Your domain can have like some smaller features, right? Like maybe this would be like a body and this would be like a hand or something. And I put nodes everywhere, right? And I connect these nodes with triangles if I am in 2D. That's what I'm drawing here. If I was in 3D, I would connect them with tetrahedrons. It will not exactly, it does not have to exactly conform to the domain, right? Because this could have been like a continuous boundary, but I want to at least approximate it well enough, okay? And I covered this whole thing. Why I drew this little thing is that sometimes somewhere here you might need some like very tiny elements, okay? And maybe somewhere over there, maybe this is something that like is not that important. Like for example, if you are simulating breathing in a human, then maybe you don't have to like simulate the stomach very much, and maybe you can cut it off and not simulate the legs at all, right? So if this is kind of like your stomach, something you're not really interested in, you can like create some like huge elements over there, right? Because for each of these degrees of freedom, for each of these red dots, you will be paying with compute time and memory. Somewhere you might need it. Somewhere you have some important fine detail structures where you want to put lots of small finite elements. Somewhere you don't care so much about the accuracy, so you can just make big ones. Like for example, at Disney, when they're like simulating a big character with like a big belly or something, they can put large elements in the belly inside and put fine elements close to the skin because they are only interested in the surface, because that's what they will be rendering, right? If you are doing a different simulation, if you are simulating how blood flows through the veins, well, then you need to put lots of small elements inside the veins, right? Because that's where you want to have your accuracy. That's actually one of the huge advantages of finite elements, that it lets you do this in a principled way. If you try to do something like this mass spring system, it gets much trickier because you will run into problems how exactly to tune the parameters for the long springs as opposed to for the tiny springs. Also, intuitively, there should be some way how the kinetic energy should account for the fact that some of the elements are much bigger than other elements, okay? If there is like a tiny guy, it still has just 3 degrees of freedom, right? But it should contribute much less to the kinetic energy than a huge guy, right? Because this accounts for a much bigger area, so will probably carry much more kinetic energy. So all these things will be done for you using finite elements. All right, so we create this mesh. There are, by the way, standard tools to create these meshes. There's triangle in 2D, there is StatGen in 3D. So there are tools you can use if you are given a mesh, how to chop it into triangles or tetrahedrons. And by the way, they wouldn't even need to be triangles or tetrahedrons. They could be hexahedrons. They could be different geometric primitives. But let's not complicate things yet. Let's keep that simple. So each of the nodes is going to have a sample of the density rho. Actually, sorry, that's not what I wanted to say. I'll do it actually a little bit differently. Each of the nodes is going to have a sample of velocity, okay, vi, and that's going to be just, let's do RD dimensional vector. The D is always 2 or 3. Just like before, each of the nodes is going to have a shape function. Okay, so shape functions, the same as before. Okay, that's going to be a functions from omega to 0, 1, such that the sum of all the shape functions is 1. So they are again interpolating the nodal values in everywhere inside the domain. That's what the shape functions are doing. Just like, exactly like in this 1D case, except that here it's in 2D and you can have it in 3D. Okay, actually I prepared an image for you to show you how the shape functions look like in 2D. It's a little bit hard to draw, so I borrowed this image. This is let's see if I can no, I cannot. So this would be my SI. Okay, this is the one-dimensional one. This is how it looks in 2D. Okay, so here I have my mesh. Here are some triangles. Here are some nodes connected with triangles. That's what this thing is. And this is a visualization of the piecewise linear shape functions. So just like here, we had the piecewise linear shape functions. Sometimes they are called tangent functions or hat functions because of their shape, these piecewise linear ones. And this is the direct generalization to a triangle mesh. Okay. So the shape function has a value 1 at its own node. Okay, so this node is node number I, and these are all the remaining nodes. The shape function will be 0, and there is going to be another shape function for all of these other nodes, and just like in this case, they all sum to 1. So that means that I can write an interpolated velocity. Similarly to before, it's just vi si p. Okay, same formula. Now it's just in higher dimensions. So in my case, I'll just say that this si's will be piecewise linear. Again, they don't have to be. They could be higher order, or they could be piecewise constant. Actually, that will be important here, the piecewise constant ones. So you got the idea of these hat functions, and that's what I use to interpolate the velocities. Okay. Now for the densities, for the rho's, let me do something simpler. Okay, and that's how it's usually done. Let me do a different finite element setup for the densities. You wouldn't have to do this. You could do the same thing, but then it would end up being much more complicated. So let's not do that. Let's do it in a simpler way. And the simpler way will be that I'll say that my rho's will be interpolated using finite elements like this. It will be a sum, and this T indexes all triangles or tetrahedra. Sometimes I call them elements. Okay, this will be the density of element T, and this will be the shape function corresponding to an element P. And this RTP, what that is a piecewise constant shape function, which is either 1 if P is in element T, so let me call this ET, and it's 0 otherwise. So this RT is a 2 or 3 dimensional analog of these piecewise constant shape functions. Okay, it's either 1 or 0. It's 1 if I'm in my element, so there is a shape function for every element. There's a shape function for every triangle. For example, if I'm this triangle, the shape function is going to be 1 on that entire triangle and 0 everywhere else. Okay, then and for every triangle, I have this RT shape function, and the T is an index going over triangles. And this rho T means that for every triangle, I am given the density. Okay, so for every triangle, I know what the density of the material in, or I could say, I guess I could say, average density of the material inside the triangle is.
So are there like 2 shape functions, one for the densities, one for the velocities?
That's exactly right, yes. There are 2, yes. One set, the ones for the densities, and those are the piecewise constant ones. So maybe let me write it here. This is piecewise constant. It's a great question. Thanks, Abhishek. So there is one set of shape functions, R's. Those are for interpolating the densities. And there is another one, the S's, for interpolating the velocities. And this is really just to simplify things, because things become much simpler with these piecewise constant ones. The problem is that I'm simulating a mesh, a tet mesh or triangle mesh. So I want my degrees of freedom to be on the vertices, right? So that's why I want these shape functions to be associated with the vertices. So that's why I need these piecewise linear shape functions to interpolate inside the domain, okay? For the density, I'm actually not simulating the density. The density is fixed, okay? I'm not doing fluid simulation or something where the density would be changing. For us, the density is fixed once and for all, okay? So I don't have to complicate things. I can just say, hey, every triangle or tetrahedron has its own fixed density. The infinite elements, that corresponds to different shape functions. But that's all good, okay? Again, by the way, notice that the sum of over all elements, this RT also sums to 1, right? Constant 1 everywhere on the domain omega. Okay, does that make sense? This is, by the way, the usual finite element setup. So this is how it's usually done in physics-based animation. It doesn't always have to be done like this. You can plug in whatever shape functions you want as long as they are reasonable. But this is the most common choice. All right, so now let's go to the fun part. And let's say that let me try to copy this. So then we apply these shape functions to our continuous thing here. So what we are gonna do, I'm gonna copy paste this. And now we have to so we are dealing with two quantities. We are dealing with the densities and the velocities. So let's first deal with the easier one. So let's first deal with the densities. Actually, the first equality is gonna be exact. So the first thing I'm gonna do, I'm gonna replace this rho p with this, okay? The sum over t, rho t, RTP. That's my approximation for the density. That's my finite element approximation for the densities. So this will be 1/2 of the integral. Let me do that very slowly. This will be the sum over t. This will be my sampled densities, and those will be the corresponding shape functions, okay? And this is still multiplied, of course, with this thing that needs to stay there, and this is now integrated over, this is still integrated over the domain. So again, I use the linearity of the integral, so I know I can rewrite it like this. So this will be, the rho t can actually go outside, right? And this will become just an integral over RTP and the squared norm of my velocities, okay? That's because this RT is no longer a function, it's just a scalar, okay? That's why it pops out of the integral. The integral is a linear mapping. Is everybody cool with that, or shall I explain that? Okay, yeah, it's a basic calculus stuff. All right, so how can we simplify this expression? Well, we can simplify it quite a bit because the RTP is a very simple function. This RTP is either 0 if I'm outside of a triangle T, and it's 1 if I'm inside a triangle T, okay? So that means that I can rewrite this entire thing like this. So I will copy this part. So all that really means is that this thing can go away, and I need to integrate this just over my element t, okay? I call this et, like here. This is my et. So that means that I'm just integrating over one triangle, or tetrahedron, and I'm integrating just this piece, okay? The square norm of the velocities. That's because this is... That's because this is 0 everywhere except for that one triangle and 1 on that triangle. So that's why I can simplify it like this. Okay? So that's one part of the finite element discretization, and now we need to work on this bit. Okay? So let me copy it over here. So now we need to figure out what the heck this thing is. Okay. Vp squared dp. So what I'm doing here is I'm integrating squared velocity over a triangle or a tetrahedron. Okay. So what I'm going to do is I'm going to apply this finite element approximation of the velocity field. Okay, so I will replace the Vp with the sum of Vi as Ip. Let's do that. So this is an integral like this, and just plug in the sum of my Vi shape functions P, this whole thing squared dP. Sounds good? I just plugged in exactly this formula. Okay, so now let me massage this a little bit. So this of course is nothing but the sum of Vi as Ip transpose, the sum of Vi as I. You know what, let me give this a different index so it doesn't get confusing. Right here I didn't use anything but that A squared is ATA. Okay. I'm just taking baby steps. Probably don't have to. I could probably do that faster, but just to make sure. So this thing is nothing but the sum over I and j. And what do I have here? I have Vi transpose Vj, Sip Sj P dP. Okay. With the transposition, I can go inside. The first sum is over i's, the second sum is over j, so it's actually a double sum. Here I have dot product, so each Vi and Vj, Vj, those are just 3D vectors or d-dimensional vectors, 2 or 3 dimensional. Okay, so this is just a scalar. And this is a product of shape functions. That's kind of the main thing I wanted you to see here, or one of the main things I wanted you to see here in this example, how this product of the shape functions appears, because that happens a lot in finite elements. So here I again, you kind of start seeing the pattern here. Here I again apply the linearity of the integral. And the fact that this Vi transpose Vj is just a scalar, not a function, so I can just plug it out of the integral. That's basically part of the linearity of the integral. And what I am left with is integrating the shape functions, actually product of two shape functions over my element. Okay? Do you agree? Cool. So this thing no longer depends on my velocity samples. This depends just on the geometry. Depends on the geometry of the triangle or tetrahedron and on the particular shape functions. Okay. So this doesn't care about the velocities of the object. So we can pre-compute this, and we can call this Sijt. The t is there because that belongs to element t. Okay. So kind of I guess that I could draw it like this. If I have some triangle here. This would be triangle number T, and this would have some indices, I don't know, 11, 17, 23, okay? And I would have two shape functions. So this Si, so the I could be 11 and J could be 17. And I have these two shape functions. They are just piecewise linear interpolating between 1 here and zeros there. That would be the, okay, let me do it slower. I think might be worth it. So if I have S11, so S11 will be, just to make sure I really get it properly. So S11 would be 1 here and 0 everywhere else, and linear ramp between them. Okay? Now if I have, here I would have S23, right? So the S23, that would be 1 here and 0 everywhere else, linear ramp between them. Okay? And this integral means, hey, integrate the product of, for example, S11 and S23. If my triangle T connects nodes 11 and 23. Okay? So now we need to compute this, which is kind of fun exercise in multivariate calculus, unless that's an oxymoron. I will not do that. I will just tell you the result, but it's actually a good exercise if you are into multivariate calculus. That's kind of a standard thing. So you are integrating, just as I explained here, you're integrating these linear functions over an arbitrary triangle. The funny thing about it is that this triangle can have any shape. It can be tiny. It can be any of these triangles, right? And the shape functions are defined on the triangle by interpolating these 1, 0, 0 values. Okay. So let me just tell you what you should get if you compute these integrals correctly. So the SIJT. So first for triangles, let me tell you both. It's actually kind of cool to compare the two. So for triangles, so that means we are in D equals 2. So then the SIJT is going to be, what do you think it's going to be? Actually, what geometric quantity of the triangle do you think it will be related to the most? It's probably a weird question to ask, but you are integrating something over a triangle, right? I don't want you to compute it right now. You can compute it later if you want to really understand this properly. But you should at least see intuitively what's going to happen. What if I was integrating a constant 1 over the triangle? What would I get? That's exactly right. Area. If it was tetrahedron, I would get the volume. Okay. It turns out that for these products, I get something very similar. So I get either, so let me call the area of the triangle, and I get AT over 3, sorry, not 3, 12. So we are, all right, we are back. Yes, you're, okay, let me write it here. Here would be S17, right? So for every triangle, we have 3 shape functions. For every tetrahedron, we have 4, because tetrahedron has 4 vertices or nodes. Actually, what do you get for tetrahedron? There where the integration is even more trickier. So for that's D equals 3, you get something actually very similar. So in that case, you will get AT divided by 10 if I equals J, or AT divided by 20 if I is not equal J. So in this case, the AT is actually the volume of that number T. Okay? The only thing it changes are these denominators. Denominator? Yeah. Or numerator. Denominator. Denominators, yeah. That's the only thing that changes between triangles, and that's also why I'm explaining that together. All right, so this is something, once you are given a TET mesh, then it's very easy to pre-compute these things, right? Because computing an area or volume is very easy. Dividing by 6, 12, 10, and 20 is also not very hard, right? So that gives you these coefficients. And then we can all write it neatly using a matrix notation. So we can write this whole thing as follows: as V transposed some matrix S T and V. Okay. So let me explain what do I mean by this notation. So I mean that into a vertex V, I just stack the individual V1, V2, and so on up to V, did I say M or N? I don't remember. Let's say N. Okay, and what is in the matrix ST? In the matrix ST is going to be exactly this. This will be the ST11 times I3, where I3 is a 3 by 3 identity. Okay. This would go all the way up to ST1N I3. This would be same idea as SN1 TI3. This would be STNN I3. Okay, so those things These guys are the coefficients we have computed. This is just a technicality, plugging in the 3x3 identities. That's this. That's just to make this matrix vector product possible, okay? All right, so this ST is a constant matrix you can pre-compute that depends just on the geometry of your mesh. Oh, by the way, I should also mention this is, by the way, just the rest pose, okay? This has nothing to do with any motion or the formation of that object, okay? We are talking about the Lagrangian formulation all the time. So whenever this is moving in space, this thing is always the same, okay? This is kind of like the reference or material space configuration, okay? So you really can pre-compute this ST once and for all, okay? Unless you start doing advanced things like plasticity, when the rest pose would actually change, the change of the actual rest pose. But that's an advanced thing. We will maybe talk about it later. Just remember, in the simple setup, this S never changes, so you can pre-compute this. In which case, this formula reduces to just this quadratic form, okay? All the velocities stacked into one big column vector, and VTSTV is the formula that corresponds. That's the finite element approximation of this continuous thing, okay? So the last thing we need to do is to plug this back in, okay? So we have, so this thing here, this VTSTV, that's this bit of that formula, okay? So maybe let me now continue over here. So I can continue like this. So this is 1/2 of sum over t, rho t. And here I can just plug in the VTSTV thing, okay? By the way, that evaluates to a scalar. So this is just one scalar times another scalar, if I even do it like this to be like super clear. Okay, I can again do a little bit of algebraic trickery to turn it into this. So there will be rho t s t and v. And this thing I can write like this. I can write this rho t s t. I can write this as a sum of matrices called MT, and the whole thing I will call M because it's a mass matrix. Okay, that's what I kind of wanted to get to. So this will be just 1/2 of V transpose mass matrix B. Okay, so what does this mean, the rho t ST? So the ST is this. Okay, that's this matrix, which is almost everywhere 0. Okay, except for the one element I'm talking about, and that element is always has the area multiplier there. Okay, it's either 0. I guess you can also imagine that the zeros would be multiplied by AT, right? Because anything multiplied by 0 is still 0. So when I multiply the area in the 2D case or the volume by the density, what do I get? Because here I have the ST matrix, right? And the ST matrix, everything is multiplied by AT. And that gets multiplied here by the density. So what I'm getting? Mass, exactly, yeah. Area times density, or volume times density, is exactly mass. And that's why this is called, this matrix M is called the mass matrix. This MT, I guess, could be like mass matrix contributions for every single element, okay? Maybe actually let me explain that a little bit better. How do you actually construct this mass matrix? Let's see if I still have time. I think I do. So I can try to explain that a little bit better. So let me actually draw this, like, say I have this triangle here. Let's say that the indices of the vertices are, I don't know, 11, 23, and 17. Okay, this is a triangle T. The T could be also some number like 15 or whatever. And then the mass matrix contribution for this element, so this empty thing, this empty that came up here, okay, so this empty is the product of the density for the element T times this ST matrix. That ST matrix, that's this guy over here. So I guess we need to kind of think about how the ST matrix looks like for this element, okay? So this empty is nothing but the rho T times AT times this matrix times this matrix. And let's think about how does this matrix look like, okay? So this matrix, let's say it's a triangle case. So I'm looking at a single triangle, okay? I'm looking at a specific triangle. So I'm only concerned about the nodal vertices, the I and j, that correspond to the nodes of the triangle. So I'm only concerned about 11, 23, and 17, okay? So here somewhere in this matrix, I will have columns 11, 17, 23, and somewhere I will have rows 11, 17, 23, okay? So those will be the corresponding values there. Everything else in that matrix is a 0, because I'm just integrating over a single element, right, over a single triangle. Remember, that's what this integral et means, that the triangle number t, okay? So all other nodal values except for the 11, 17, and 23, they are irrelevant, so they are 0. Okay, they don't contribute to the integral over that element. I already put the AT outside, so what will be these values over here in this matrix? That's exactly what's written here. It will be either 1/6 or 1/12. Where is gonna be the 1/6 and where is gonna be the 1/12?
1/6.
Correct, Trevor. Or maybe someone else said that too. 1/6 is gonna be here, and 1/12 is gonna be on the off diagonal. So here again 1/12 and 1/6 on the diagonal, 1/12 off diagonal, 1/12, 1/12, 1/6. Okay, that's because this, for if I equals j, we are on the diagonal. If I not equals j, we are off the diagonal. Okay. And this is how you build the entire mass matrix. The entire mass matrix is nothing but the sum of the MTs for all the elements T. So this is the big M. So this is for a single triangle, right? For another triangle is gonna scatter another 3 by 3 kind of thing. You sum all of them together. That's your complete mass matrix. Okay. So what properties do these mass matrices have? They are symmetric. That's very important. Yes, M is symmetric. There is another important property we talked about a lot recently.
Invertible.
So it usually is invertible, but it's invertible only under certain assumptions to be like really like pedantic, I guess. For example, if I told you that the density is 0 or that some of the areas of the triangles is 0, it wouldn't be invertible. So you just need to make the assumption that none of these elements is actually non-degenerate. You kind of take it for granted until your meshing software actually creates you some elements with area 0. So that's something you want to check for in your code, okay? And when you are, of course, choosing the densities for all the elements, you shouldn't give it 0. You should not give it a negative value, because that's not a good density, okay?
Be non-negative as well.
Correct. It's gonna be non-negative. So if you make those, so it's gonna be always positive semi-definite. Because there cannot be any negative numbers. Okay, that immediately implies it's positive semi-definite. If you want to be positive definite, then you need to be a little bit careful and make those assumptions that none of the elements is degenerated, that it would have 0 area or volume, and that none of the densities would be exactly 0. Right? And this is something you almost always want to make sure in your code, even if it's not exactly 0, even if one of the elements is so tiny that's like on the boundaries of numerical precision, that's no good. Okay. By the way, the software that usually creates these meshes for you, the metric for the quality of the software is the quality of the shape of those elements. Because if you get a tiny little sliver, kind of like this, maybe I have some another vertex over here, right? Then I get a crappy element like this that's gonna have like a very tiny area or volume, even though it's like very long. So those elements are no good, okay? So they can basically create numerical problems in the simulation. But I guess I digressed from the properties of the mass matrix. So notice, and also notice what is the sparsity structure of this matrix. We talked before that it's very important to exploit sparsity. And this matrix is very sparse, right? Actually, how sparse is it? Correct. Yeah. Okay. I guess actually, you reminded me one thing I forgot, right? I should have written here times I3 everywhere, right? Because I forgot about that little detail that I actually need to put the 3x3 identities everywhere. So if you forgot about those and just look at the scalar values there, what is the sparsity pattern of the matrix? Or how many non-zeros does it have?
2/3 of it is, or 1/3 is non-zero.
Oh no, many more is non-zero than 1/3. Look, this could have been 10,000 by 10,000 matrix and only has 9 non-zeros in it. It actually doesn't matter how many degrees of freedom you have, right? Like here I already drew like 20. You can have a million nodes there, and this MT is always gonna just have 9 non-zeros. And if you actually sum it with other MTs, right? Like next to this will be probably some other triangle, right? Well, I don't know, 18 or something. And this will have actually similar pattern, right? This will just hit the 11, 18, and 23. So actually, it will not add 9 new non-zeros because some of them already overlap. It's going to be hitting some of the non-zeros already there. Okay? So the sparsity pattern for the entire M is going to be like this. So it's going to be it's going to be 1 if, or I guess I could write Mij, right? Either if I equals j or I and j connected by an h. Okay, it's gonna be 0 otherwise. Okay, so for every row of the matrix, every row corresponds to some node. So the number of non-zeros is the number of edges emanating from that node, which is typically 6 for triangle meshes, by the way. So the number of non-zeros of this matrix is going to be something like 6n, when n is the number of nodes you have there, okay? Which means that it's almost completely empty, by the way, because the matrix would have all number of elements is n squared, right? But if you have only 6n non-zeros, then you kind of must take advantage of this, right? Otherwise, you are storing in memory lots of zeros for no good reason. What people often do here is to say we actually want to simplify this even further. Like they say, oh, even this is kind of too complicated. And it sometimes is. Like if you want to be inverting this matrix, it gets not super complicated, but it gets a little bit annoying. So sometimes it bothers some people, sometimes no problem. Sometimes it bothers people, in which case they say we will do mass lumping. And you will hear this when you are reading some papers about finite elements. You will just hear that they do mass lumping, because that's kind of what everybody does. And what that means is that we approximate this M matrix with a matrix M tilde, where the M tilde is almost the same thing as this. So the M tilde is kind of built from all MT tildes, which are approximations to this matrix. And they're approximating this with the diagonal. Okay, so the MT tilde is rho T AT. And what we are going to say here, we will say screw those off-diagonal elements. Exactly what we're going to say. Okay, and by screwing, I mean that we will add them to the diagonal. Okay, so on the diagonal, so off-diagonal, I have 112, 112, right? So that means 2 12s, meaning 1/6. So I will add this instead to the diagonal. So I'll have 1/6 plus 1/6, that's 2/6, aka 1/3. Okay? So I will put there 1/3 again of I3 at the coordinates 11 and 11 in this example. I'll do the same thing for the other one. So 1/3 of I3 and 1/3 of I3 for the other ones. Okay, this would be like the 17 index, this would be the 23 one. Okay, this process is called mass lumping, and what you get out of it, of course, is a diagonal mass matrix. So that's much easier to deal with, and it turns out that usually you don't lose almost anything if you do this. People done experiments when they were comparing the lumped and non-lumped mass matrices. It turns out that the lumped one works just as well, so you might as well use that. Now, strictly speaking, it's less accurate because you are throwing away. This is actually the real deal. That's what came out from finite elements. This is kind of a hack. And I guess next time I'll explain you what is the finite element, or you can think about it for next time. I will ask you, what is the finite element interpretation of this hack? And the hint is that you could get this lumped mass matrix also formally by using finite elements. And for exercise, you can think about how you could get the lumped matrix, not by hacking this matrix, but by applying the finite element framework with a little bit different shape functions. Okay, that's like a thing for you to turn on until the next lecture. For now, let me just tell you how does it look like for, this was all for triangles. For that, it's actually very similar. For that, the non-lumped one would look like this, right? That would be the same idea, except that you would have some 1/10 or I3/10, and here you would have I3 divided by 20, I3 divided by 20, so it would be I3 divided by 20. Now we are talking about a tetrahedron, so it has 4 vertices, right? So now we have 4x4 block, and again it would be I30 divided by 20, I30 divided by 10, I30 divided by 20, I30 divided by 20, and so on, okay? Same idea, slightly different values, okay? If you do the lumping, here, then you approximate this with rho t, a t, and guess how much this is if you lump it. You do 3 divided by 20 plus 2 divided by 20, so you have 5/20, which is 1/4, okay? So we'll get 1/4 of I3, 1/4 of I3, and two other ones, okay? That's the lumping for the case of tetrahedrons. And by the way, the code to compute this lumped mass matrix is actually super easy and super intuitive. The code looks like this. You do a loop over all elements, over all t's. You compute the mass of every element. That's this rho t, a t. Okay, so you compute the area or volume in this case, multiplied by the density. That gives you the mass of the single triangle or tetrahedron worth of matter. Okay. And then what you do in the 2D case, you divide it in 3, and each of the nodes gets third of the mass of that element. Okay, so here it's like super intuitive. You could like imagine here, I kind of chop it in like 3 pieces here. One piece would be blue, one piece would be green, one piece would be red, and each of the vertices gets the 1/3 of the total mass of those pieces. That's really what this matrix is saying. Okay, and then you sum all these matrices for all the elements, and that means that you do this loop. So this element gets 1/3 of this triangle, then it would get 1/3 of that triangle, 1/3 of the mass of that triangle, and so on. Okay, there might be some other triangles connected to that too. So like the math to get there is kind of complicated, but the code to actually compute the lumped mass, the non-lumped would not be much more complicated, right? You would just put the 1/6 and 1/12, and then just do sum. So again, you would do a loop over all elements, right? And each of the elements would scatter these values into the global matrix M you are computing, and you just add it all together. All right, and I think this is a good point to stop. I have one more thing to tell you, which is how do you get directly the mass matrix from the lump mass matrix directly from finite elements, but I'll tell you, you can think about it till next time. And then there is one more trick, is how do you plug this into the Hamiltonian framework? Okay, what does this change in terms of the Hamiltonian? There is like a little trick I need to tell you. And once we are done with all that, then we will talk about how to apply the finite element discretization to elastic potentials, which is even more funny than this kinetic one. Because at this point, we'll need to talk about material models, constitutive materials, and continuum mechanics of solids. So that's for next week. All right, any questions? If not, we will end here.